So I'm Simon. I'm faculty at the University of Washington, and I'm an operating systems researcher. And what I'm going to introduce now is a project that we have started within the FOCI Center to try and address from software systems, but perhaps also hardware software co-design perspective, some of the problems that we have been talking about in this workshop. Specifically, this is almost a recap, I would say, of many of the problems that came up earlier. We have this kind of rising cost of power infrastructure, which is creating a problem for data centers because we want to reduce that cost by oversubscribing power. But also we have this problem from the utility side, where they're now in certain regions requiring us to provide demand response, so being able to modulate our power demand, because for the utility, the cost of provisioning the power to the data center is too expensive. Of course, we also have this drive towards renewable energy. Many of the data center operators want to be fully renewable very, very soon. And with renewable energy comes more supply variability, because the production of, in particular, wind and solar is inherently variable. Finally, we also have kind of a want for resilient operations and logistics of data centers. Namely, when we build a data center, we're not always perfectly able to predict the workload. In fact, in many cases, and we've seen this most recently with large language models, before that, I would say the kind of top of mind was COVID, create various demand spikes for data centers. And we might simply not have the power to provision the compute necessary to handle the demand. So we may actually be able to put more servers into the data center, but powering them is really becoming a main problem. And finally, we've talked about this as well. We also see increasing power disruption on the grid, leading to more blackouts. And so from a data center operations perspective, we've distilled these into these three power charts that we have here on the right. At the top is the variable supply, where we may have a mix of, say, renewables and fossil fuels. We want to make optimal use of that mix. When renewables are available in abundance, we would ideally want to ramp up our load within the data center in order to use them. And if they're not available, then in order to stay green, we would like to ramp down the load. Not something that is very much possible today in a data center. In order to handle these demand spikes, we would like to kind of smooth out the load of the power load within the data center, so that we can actually direct the power that we have to the servers and the accelerators and other heterogeneous devices to handle those demand spikes. And then finally, we have the blackout situation, where we have a limited amount of time running off reserve power. And ideally, because many data centers are actually involved in kind of first responders getting situational awareness, we would like to outlive blackout periods longer than the reserve power that we may have available within a data center. And so our plan is to try and make cloud power demand software defined, essentially build a control plane. And think of this very similar to how we've been making networking and other things in the data center software defined, to be able to react and respond to these supply situations and demand situations from a workload demand perspective, to modulate the load within the data center. In order to do that, we need to build a load to power feedback loop through the hardware and software stack. So you can tell here this will involve many of the kind of runtime systems, including operating systems and so forth, but perhaps also new hardware extensions. Isha already talked about a number of them that are possible, that haven't yet been realized on the GPU side, for example, but there are likely also others just within general servers and on the CPU side and other accelerators that will need to happen in order to make this work efficiently. And once we have this, we can then build a large-scale power control plane for the data center that can execute automated power control policies at scale, that would then allow us to gracefully trade off power, performance, and of course, quality of service under the SLAs that we have for the applications, in order to modulate our power demands to respond to these different situations that are laid out on the previous slide. And so that is what we're intending to do. We're building mPower, which is short for Elastic Management of Power, which will be this control plane, as well as all the different software and hardware solutions to make this a reality. Essentially, Empower should be able to observe and control power demand at fine granularity and over short timescales. The finer and the shorter, the better, because that would allow us to react better to unforeseen situations and also control workloads at the granularity that we would need in order to maximize the modulation of power that we desire. And then we can use this to leverage the application. I call it SLA slack, effectively the slack that we have within an SLA of an application to consolidate and shed some load, move it around, time shift it, and so forth within those SLAs that we have. And then once we have that, we can power switch hardware components, set them into lower power modes more efficiently than before. And I said the other points here already of migrating the critical loads to perhaps lower power processors. This is maybe just one thing to note here, such that we can reduce the power for those workloads where that works, as well as, say, power switch storage devices and so forth. There will be a talk later about this as well by Dedong. And so with that, we are then able to kind of introduce this notion of shiftable demand to address these power problems that are laid out earlier and smooth our power demand curves. We have identified a number of challenges in building this new power control plane. First and foremost is that we currently don't have good tools for power provenance in the data center. And this is something that Jonggyu, who's going after me, is going to talk more about. Essentially, right now in data centers, we have power instrumentation only really at the chassis and at the socket level. What we would ideally want is per process or even per RPC, per remote procedure call, power provenance, so that we can identify which of the different loads we consume the most power and in which ways, so that we can then move them away or perhaps shed them in order to save power. I just want to have a quick eye here on the chat to make sure I'm not missing anything. No. The second one is that there's, while there's relatively, I would say, not adequate, but rudimentary power control at the CPU socket level and core level via technologies such as dynamic voltage and frequency scaling, DVFS, as well as RAPL, which is the kind of socket level power monitoring and control mechanism that Intel has been producing to ramp up and down also the power of memory. There is limited integration with accelerators and other devices within servers. So we did a measurement study to analyze the power proportionality of servers in a variety of data centers today. And we found that server power proportionality has actually been going down. It's been getting worse. Servers can consume idle power when there's nothing running on their CPUs, up to 220 watts for regular servers that don't have GPUs in them, and even up to 600 watts for servers with GPUs in them. And main reason for this is that many of these other devices that we're now increasingly integrating into servers, such as those GPUs, but also storage devices, SmartNICs, other infrastructure accelerators, are not currently particularly power proportional. And so we need to build this knowledge to understand how they're using their power and ultimately build mechanisms for them to control their power better. As these hardware devices are becoming more power proportional, we then need to make our operating systems and other runtimes fit to actually coordinate this power consumption that we have across all of these devices. It's not enough to just have individual devices being able to ramp up and down their power demand. Instead, we would have a bigger power savings if we were to have an operating system or other controller actually coordinate the way that workloads use all of these different components of a computing system and of a whole cluster in concert. And so this is another thing that we need to work on. And finally, of course, we have to solve the kind of fundamental problem of making all of this work at scale and still keeping all the fine granularity and the short time scales that we need in order to make this an efficient reality. And I forgot to mention that Dedong is going to give a talk after Jonggyu to talk a bit about integration, in particular with storage devices. So here I have a kind of 10,000-foot high-level overview of what we intend to build. It's probably best to explain this slide from the outside in. So maybe I'll start here at the top. So ultimately, what we intend to build is a master controller. So this would be a piece of software that runs on a set of servers in the data center that takes in power budget info at the highest level from the utility and from other power devices that are connected to the data center at scale. This could also include warnings from the utility if there's a power event coming up, and it takes this data. It also takes data from the operations of the data center itself. So this would be data that has been measured directly in the various components, so at the servers, perhaps also at the switches, and then down into the various components of each of these different servers. It collects all of this information and the workload demands on the data center, and then out of that computes power budgets for a variety of different clusters down into the servers of our data center, and then distributes those out across the network to the operating systems that are running on our servers. And so the operating systems are then involved in addition to, of course, characterizing the power to feed to the the master controller, to control the power of these different devices and servers within the data center, perhaps even all the way down to putting a server to sleep in order to maximize the power savings. We heard earlier that fans are actually also a major consumer of server power, even when the server is completely idle. And those fans are running no matter whether the server has something to do. And so that factors quite prominently into the idle power consumption of each server. But of course, the operating system also should then go on and do fine-grained power control of not just memory and CPUs, but also of all the other devices and accelerators that are now included within a server. And with this kind of trend towards disaggregation, we could even go as far as shutting down the kind of CPU part of a server and offload amenable workloads to low power types of heterogeneous compute, like these smart NICs, for example, where they can still do useful work for the kind of urgent tasks that a particular application may require, but don't consume nearly as much power as the server, when it was fully running, would consume. And so I'm going to summarize here to give Jonggyu and Dedong some time to go into further details about this project. So data center power variability is increasingly a problem. We've heard it already variously within this workshop. And our goal is to make data center power software defined to allow us to gracefully trade off power, performance, and quality of service under SLA. And so we're building Empower, a power control plane at scale for the data center, which would then bring about fine-grained and coordinated power instrumentation and control at scale to enhance the power control dynamic range while keeping the same SLAs for those critical workloads that we're running within our data centers. So thanks, and I'll take any questions while Jonggyu sets up his slideshare.
I have a quick question, Simon. This is John Kumi. It sounds like you did some measurements of the idle power of different servers. Right. Did you also do it for ML nodes and for GPUs, or was it just the general purpose devices?
Yeah, both. So that's why I kind of broke that out. So we had the kind of general servers that were the ones that were in the kind of 200, 250 watt range. And then the GPU servers have massively higher idle power consumption due to the fact that the GPUs themselves are not yet quite at that level of power proportionality that we're kind of gotten used to on the CPU side.
And did you do these measurements kind of in the data center once the devices were used, or was it more kind of, this is how the device was shipped, and here's how it is measured using spec power or some other, or CERT or one of these other ones?
So these were in situ measurements in a variety of data centers that we had access to. And then we also talked a little bit to the kind of hyperscale cloud providers to see what they see in terms of idle power, just to kind of confirm what we're observing with our measurement study.
So did you publish these? Because I would love to refer to these. They're
not yet public,
really...
but we're working on it.
Well, so an interesting question as you finish the write-up. I've always thought that the measurement kind of as shipped would differ from the measurement in situ, as you said, because every data center manager I've ever talked to says, oh yeah, all that power management stuff that Intel spent so much time working on, we just turn it all off when we get it into the data center. And that's not universally true. And some of the things are not subject to user choice. But my guess is that the beautiful idle power, closer to energy proportional measurements that you get as shipped are not the same as what you actually see in the field. And if you have data that would allow us to get at that question, I think that would be incredibly important for the industry to see, because there are ways to fix that, but you have to know that it's a problem first.
Indeed, yes. And perhaps Jonggyu and Dedong, since you have done measurements both on the kind of servers and storage side of things, you may want to maybe at the end of your presentations talk a little bit more about what you have seen as you've been doing the in situ measurements compared to the spec sheets.
Brilliant. Thank you so much.
Thank you, John. Okay, I'll hand it over to Jonggyu, who is working in the FOCI lab. He's a postdoc on his first year being a postdoc. And he has been investigating this question of how can we attribute power draw to individual applications to make more informed decisions as to what loads we may want to migrate off of a particular server. And it's called PowerTrace. So Jonggyu, please take it away.
Thanks for the introduction. Hi, I'm Jonggyu. I'm a postdoc researcher working with Tom and Simon. Here, I'm going to talk about our recent project to improve observability on CPU power consumption, PowerTrace. PowerTrace is a software-based tool that estimates the CPU power consumption in a unit of application or process or other various granularity. The conventional approach to accurately measure CPU power is mostly done by using hardware monitoring tools such as RAPL. However, the current RAPL provides only the level of sockets or packages instead of per application or per process. So it is unable to figure out how much power an individual application or container is consuming. Also, there is a security issue in a cloud setting. If we directly expose such global CPU power values to cloud tenants, this can be exploited as a side channel attack, because some tenants might get some power information that are not there, where they are not using, but they get some power information from other VMs or containers. To overcome such problems, our goal is to build a new open source software power estimation tool that provides finer grained power estimation without using RAPL in real time. Our tool clarifies what applications are currently running and attribute power to individual applications by utilizing various CPU-related information, such as various CPU states and other performance counters obtained from perf command. For example, as shown in the figure, when we run Redis with a microservice, the tool can actually report the power consumption of each program individually, in addition to the entire CPU power consumption, without actually using RAPL. I will introduce some difficulties we have encountered when it comes to power estimation. Since modern CPU architectures adopt per core P states and C states and DVFS technology. Here, the P states means active states where the cores are actually doing some tasks. And C states means idle states that are not doing any computation. But the problem is the CPU power consumption is varies depending on the CPU states. For example, even if cores are on C states, depending on what kind of C states, the power draw is significantly different as shown in the figure. And the same rule applies to the P states too. And such power consumption is not just linear, which complicates estimation process. Also, there are multiple factors we need to consider since CPU power consumption is not solely determined by a single factor, but multiple CPU statistics, including cycles and branch misses, etc. So we've also selected the important CPU statistics that are related to CPU power consumption by performing some machine learning sensitivity tests. Here are the lists that we've obtained, decided to use in our tool across by analyzing such metrics across multiple different architectures, including Intel and AMD ones. In addition to them, The thread affinity on sockets and cores also matters, since some unused cores can individually go into sleep states so that the CPU can save some power. And such CPU states are individually controlled. Also, depending on what kind of threads are sharing the hyperthreaded cores or sockets, the power profile can be different. So this also complicates CPU power estimation, since we need to consider such per core information to accurately estimate the CPU power. Considering such many factors, we have built PowerTrace that collects various per core CPU information, including P states and C states, and frequency of individual cores, and other CPU statistics, including cycles and branch misses and instruction count, etc. Also, we collect the ground truth CPU power values from REPL only for the training purpose. Afterward, we use it for estimating and attributing power to applications. For training, we stress various system components, including CPU, memory, I/O, and etc., with various test scenarios to diversify test cases while collecting CPU-related data as machine learning features. We've tested various machine learning models, including tree-based ones and linear ones, but we've decided to use CapBoost considering the feature map data structures and the efficiency and accuracy of the machine learning models. Here's the evaluation of our tool using real-world applications, including microservices that are not included in the training data. So we collected such real-world application trace, and we solely used it only for testing data other than training data. The leftmost column only collects the CPU states, including P state and C state, and average frequency of per core information. And the second one collects only perf data, including such as like cycles and instruction count and branch misses and so on. And PowerTrace here gathers both of them. We estimated power using all three different cases while collecting ground truth from REPL, and the PowerTrace shows the best accuracy out of all three methods by showing around 4% errors. This shows not only considering CPU statistics, also it matters to collect such per core P state and C state information as long as along with frequency information too. So far, we verified the accuracy of our machine learning model, comparing the estimated power with ground truth. We leverage this machine learning model not only for estimating the entire CPU power consumption, but also in the process of power attribution to application. For attribution, we collect per core machine learning features and figure out the core occupation information of applications and build a feature map for each individual application. For example, here, if application A is currently occupying core 0 and 1, we combine such cores features and create a new feature map only for application A. Similarly, we do the same for all the applications that are currently running in the system, so that each application can have their own feature map, which describes the behavior of CPU activities used by the particular applications. Afterward, we estimate individual application CPU power using their individual feature maps and the pre-trained CapBoost and machine learning model. After that, we normalize the estimated per application power by socket power. And the total socket power is also obtained via our machine learning model instead of using REPL in real time. So our tool does not rely on REPL at all after the training process, so that we expect the tool can be used in inside virtual machine or inside containers. By doing so, we can estimate the CPU power consumption of individual applications. Here is the evaluation results while running two different workloads CPU and matrix operations from a synthetic benchmark. Each application here is physically isolated to each socket to minimize any performance or power interference. We also added the ground truth from RAPL here and combined active power in the figure to verify the accuracy. As you can see, our tool shows pretty accurate power estimation by showing around less than 2% of errors when it comes to total active power. And regarding attribution, since we don't have ground truth for individual applications power, we indirectly verify the accuracy of attribution by terminating CPU workload and see if the power consumption of the other application continues the same. After terminating the CPU workload, our tool continues to estimate the power of matrix workload with less than 2% of errors. This shows that our tool also can be used to predict the power changes in advance before we actually terminate or change some applications when the applications are physically isolated. In conclusion, I introduced our new power estimation tool called PowerTrace. And we also have verified our tool across multiple CPU architectures and showed less than 10% of errors when the training data and test data are from entirely from different sets. Our next steps are developing a model that can estimate the effect of process and container scheduling and building a new power optimizing CPU schedulers. In addition to that, we are also planning to make it even more finer grained to figure out power consumption of functions or RPCs. The source code is available here, and you can really try the tool at this link. And thanks for listening. I'll take some questions if you have.
Thank you, Jonggyu. We have time for a question or two.
Yeah. How much of the power consumption depends on the workload and how much of it is intrinsic to the application? So for example, if you were measuring this on Redis, if you change the data set and if you change the access patterns, how much variability do you observe? Did you do some kind of study like this?
I didn't directly compare depending on the configuration or things, but in my experience, I mean, depending on the application or within the application, depending on the configuration and depending on the number of cores, depending on the threads, the power changes like a lot differently. So I might say like it's gonna be more than like 50% difference depending on the number of threads. So the primary the factor that determines the power is how actively the cores are running and how much the application is optimized in terms of like parallelism and the number of cores and the number of threads. So it really depends on the application's optimization point. If this is highly parallelized and then they use a lot of CPU operations without sleeping, then they, of course, like the power consumption will significantly change as the number of threads changes. But other than that, if the application is not optimized and they are not using the CPUs well, the CPU power consumption won't be that much difference. Depending on the configuration, from my experience.
I see. Okay, thanks.
Thank you, Jonggyu.
I think before we move on to, I have one question too. I think, have you tested with the hyperthreading on?
Oh, those are all hyperthreaded enabled.
All hyperthreading enabled. So I think once you turn that off, like you still model looks good.
I guess the hyperthread actually complicates the estimation process. Why we also consider what kind of cores are co-located within the physical core. But I guess if we disable hyperthreading, it might work better than now, I guess. Because because of the hyperthreading, it actually decreased the accuracy.
Yeah, so hyperthreading one of the good parameters when you do the power estimation. Anyway, so I think if you take a look at it, that's good.
Yeah, thank you.
All right.
Okay, and next up we have Dedong, who is a first-year grad student in the FOCI lab at UW, and he is looking at power adaptive storage systems. Dedong, please take it away.
Hey, thanks, Simon. I'm Dedong here. I'm a first-year PhD student at University of Washington. Today, I'm going to present our work on power adaptive storage systems. This is a work really in its early stages, and so far we have measurement studies that performed the last quarter, and we draw some design insights we learned from the measurements, and we seek your input. So currently, storage is a significant power consumer. For an average data center, the storage system accounts for 10% of the total power consumption, while in a hyperscale data center, we can see the share of infrastructure will be lower, and so the share of the other components will be even higher. In 2021, the storage in data centers was estimated to use around 20 terawatt hour of power worldwide. So looking into the future, the storage power draw is unlikely to decrease. Data center storage have seen a trend that SSD replacing HDDs, so that SSD is taking a bigger and bigger part of storage devices. We can see from the latest HDDs and SSDs, there's an interesting consequence is that SSDs will use a higher active power while the idle power of the two devices are coming close. To achieve the same capacity, the SSDs will use 7 times more active power, while it's 2 times the idle power. So if this trend is ongoing, then the power used by storage is going to increase. Since storage system is a major power consumer in data centers, to achieve our goal of making a power adaptive data center, as mentioned in Simon's talk, storage system also has to be power adaptive. But currently, storage systems are not power adaptive enough. There are two mechanisms we can make use to achieve power adaptivity in storage systems. The first one is to control the power state of storage devices. And the second one is to manage the data access operations to the storage devices. For the first aspect of controlling the power states of different storage devices, we can try to put idle disk to low power standby or completely cut off the power. We can also enforce a power caps on SSDs when the power is constrained. For the second aspect of managing data access operations to storage devices, we can consolidate I/O requests to maximize the idle periods. We can also tune I/O trunk sizes for each I/O instructions we issue to the storage devices, and we can avoid the transfer from SSD to HDDs because HDDs takes a larger idle power. To validate these ideas of controlling power usage of the storage system, we need to get the data on how these operations influence storage devices, both SSDs and HDDs, of their power draw and the performance. So we conduct this power consumption measurement that in order to get those power characteristics of the storage devices. We first separate the power supply from the storage devices using a separate power supply unit, and we measure the power drawn by the device from its power wires. We aim to achieve a high sample rate and also a high resolution. So here we use a microcontroller and an oscilloscope to sample our data from the power wires of the surround registers, which achieves 30,000 hertz with microcontroller and with 1 gigahertz with oscilloscope. While we also achieve a high resolution of the power data, we can measure at 0.3 microvolt with an error range less than or equal to 1%. Then we use this measurement infrastructure to get the power consumption characteristics of SSDs and also HDDs. So one thing we can think of controlling power is to put the devices that in the idle state to an even low power standby mode. Our observations show that after spin down, HDDs can use less than 1 watts. And there is also a factor of 10 times of power savings for SSDs if we put it into a low power standby state. However, this power saving is at a cost. The transition time between the low power standby and active I/O modes for HDDs is 100 times longer than the same transition time for SSDs. So we draw the following design implications that we can put in idle disk into the low power standby mode, but we have to figure out some way to not put HDD to standby too often or find some way to mask this latency. The second thing we can do to control the power usage of the storage devices is that we can enforce a power capping on SSDs. And here we observe that if we cap the SSD's power from 25 watts to 21 watts, there is negligible loss in the read speed, while there's a 30% downgrade in the speed of writing to the SSD. If we take really aggressively power capping to the main active power state of 9 watts, there is a 20 times drop in the read speed, while a 10 times drop in the write speed to the SSD. From these observations, we have the following design implication that we can apply the power capping on SSD, but we have to do it depending on the workload characteristics. Another thing that we have control over in the storage system is the I/O trunk sizes, which we write to the storage devices. Our observations are as follows. For small I/O trunk sizes, it can reduce average power during the I/O by 30%. But compared with medium-sized transfers, the small-size transfers takes much longer to complete to transfer the same amount of data. So on HDDs, the small-size transfers uses 100 times more power per byte transferred, and on SSDs, a similar trend of 3.5 or 7 times more energy used. So this draws design implications that we can use the larger trunks or small trunks to control the power usage, while consolidated small I/O requests to reduce total energy use is also promising. So based on our observations of the storage device's power characteristics, as we listed before, we propose this possible system design. We plan to design our storage system controller as a part of disaggregated storage cluster, and we use the interface with the EM power control plane as mentioned in our general goal described by the Sam's talk, which the EM power control plane will tell us each storage cluster how much energy budget it can have, and also it will get back feedback from the clusters to get for the further power budget allocations. The storage clusters then will work under the power budget have been given by control the device power states, but employs the power cappings, and adapts its I/O trunk sizes issued to the storage devices. So in conclusion, we see that power adaptive storage is a critical part to a power adaptive data center. There are some mechanisms for power adaptive storage, which are like we listed, including controlling the device power states and managing the I/O access patterns. And furthermore, our measurements on the SSD on HDD power characteristics showed how to use those proposed power measurement techniques like tuning I/O trunk sizes, change power states, and also enforce a power capping. While there are still some questions that remains to answer, like what technology will future storage devices use, and how will future devices fit into our system? And will these future storage devices have the features that can help our system to achieve even higher power dynamic range? And lastly, if we can effectively influence the future devices towards a more power management features so that our system can work even better. So this concludes my presentation. Thank you.
Thank you, Dedong.